gonna start over here. You should be able to see the screen and everything. And let's get right into it. So some of these integrals, again, they're gonna need some editing, right? They're not gonna be able to just plug and chug or evaluate them in order. So the first one I wanna look at is 6a over here, starting easy and then developing more and more and more. So this is an integral, it says, that goes from 0 to pi over 2 and from 0 pi over, or actually from x to pi over 2. We're gonna have to mind the integrand right now because that is, again, the way this is written right now, not possible. So I'll tell you why. There is no way that we can integrate this bit with fundamental functions. It's just, you can try any substitution, any trick from the book that you know, like trig sub, u sub, whatever the heck you want. You can try it and see that you will not be able to actually do anything. So how do I fix that, right? Well, the way I fix that is by sketching the actual integrand, the space that we're going to integrate this function. We have to, in 2D and 3D integrals, we have to. It's no longer a simple line that we're integrating, it's a whole field. So we have to see again how this integrand looks like and understand it. Now, to do that over here, I'll go, it's a double integral and it's happening in the YX plane. And what do I see on my integrand? I see that my y, the first one here, the first integral is the y integral, right? And I see that my y, it says that it's going from y equals x and it's going to y equals pi over 2. Okay, so that's not a big deal. We can understand how this looks like. And then once I have the integrand with respect to y done, I look at the one with respect to x and it goes from 0 to pi over 2. So again, for x here, we go from 0 to pi over 2. And these observations you want to put down on your plot. That's like what you're aiming to do here. So I go in, what does this look like? Let's ask Kelly, what is this? What does this thing look like? I forgot Kelly's outside. Hold on, she might not be able to talk. So I'll assign that to Olivia for the time being.
Oh, it's just like the line y equals x.
Okay, gotcha. So there it is, y equals x. And you're telling us that we're gonna have to integrate in the y above this and until this, right? So if you're doing this vertically, right, I'm just telling you, you'll have to do the integral here. Let's just put it like this. So we're gonna have to do the integral again until the value of pi over 2 in the y direction, okay? So we're integrating like this in the y, and we only reach pi over 2. And then for the x direction, you can see it very well what we do here. We go from 0, right? As we do the x integral, we go from 0 all the way to pi over 2 in the x. Now, hold on a sec, okay? You have to be careful. You have to be mindful of our bounds. If right now, the integrand space goes from x equals 0 to pi over 2, notice again what the actual result is going to be. It's going to be a square, right? Like if I was to extend these blue lines from 0 to pi over 2, we're going to rather define a square right now. Do you see it? Right? That's a little bit, yeah, like that's what would happen if I went from, again, y value here from 0 to pi over 2, and then I turned right and went from x equals to 0 to pi over 2. So how do you prevent this? Right? You might be thinking, how do you prevent this? The order matters that you write the integral right now. So let me explain. Okay, let's say that I switch the order right now and I do this integral first. Well, this integral, as you can see, would take me from x equals 0 to pi over 2, like I did the blue arrows, right? That would be the integrand space. And then if I went from y equals x to y equals pi over 2, that makes actually no sense, right? Because I will have a variable by the end of my integration, right? My integrand is going to be a variable that I'm going to have at the end. But I know that this has to give me some value. You know what the problem is right now that I switched the order? It's basically you doing this. And what have I said before about integrals that have a variable that is getting integrated? I've said to do them first. Remember that. They gotta get done first. And in fact, you will see every single time you do an integral, it's always going to be the very outside, like the very last guy that's going to be evaluated between numbers. The in-between guys, like if it's a triple integral, the first two integrals are going to be variables usually, and then the last one will be a value. So be careful not to mess the order up. So we're going to keep that order. And again, that forces me to think of the integral like this. First, we're going to do this move, okay? And I'm saying with the second integral, let me explain what the second integral says. The second integral says right now that we're going to stop here, okay? We're going to stop at or x equals pi over 2. We're not going to continue here because it could have been the case that I continue on, right? Got to continue on. So we're telling ourselves that we're stopping there. We're stopping that y integration that you see. The integration's happening in the y like this, right? Up to pi over 2 like that. But we're going to stop as soon as I hit this guy right here. We're going to stop because I could have kept going. Now, in this unique scenario, in this unique integral, because this is pi over 2 and this is pi over 2, the end bound of the x integral, I would have had to stop there regardless, you know, because that's the line right there that I have to stop at. And this corresponds to x equals pi over 2 anyways, right? You would have had to stop there anyways. But it could have been the case, let me show you a different integration. It could have been the case that you're doing it up to there, right? In which case those arrows go further up, right? And you could have had to stop, for example, all the way out there, right? All the way out here. So that would not be included if you were going from x equals 0 to x equals pi over 2. That would have been the part here that you exclude right now. So luckily in this integral, that thing does not happen right now. So, you know, the accidentally, you know, this is actually accidental. At least I believe so. This is accidental that this pi over 2 and this pi over 2 are there. Okay, it could have been different. But now you have an idea of what the integration looks like in the space that we're going to integrate this function here, this f of x, y. Okay, this f of x, y, we're going to integrate it in this space. Now, I told you that this way, not good. Okay, not good. We can't do this integral right now. So what do we do instead? What if I change the order that I do this? Okay, so change my x's into y's and retry and see if I can get away with it. Okay, so just change the order, shuffle it around right now. This helped me construct the plot. Now that I have the plot, maybe I can create a new integrand bounds over here that will switch the order. So I'll have dx first and dy second. I'll switch the order. Okay, and maybe I can avoid that problem. Let's see. If I did the integration in this direction right now, okay, so I'm going to redraw here a diagram. I want you to see the difference. If I did the integration in the x direction, so my arrows pointed to the right, what would happen now? Look at my x value. It goes from 0, right, not to pi over 2, but rather, who is defining the boundary here? Let's ask Leah, as a, you know, to get you girls involved a little bit. Who's stopping the integration in the x right now? What do you think, Leah?
Like the pi over 2 bound in the x.
Not the pi over 2 bound, because that would mean that we're going all the way out here, right?
Oh, sorry, the like y equals x bound.
Right. But because we're talking about the x world right now, this turns the other way around right now into this. Okay. So we're saying that we're basically going, the blue arrows here, we're saying that we're basically going from x equals 0 all the way to x equals y, basically. You see that? And then for our y values, we can clearly see those right now. For our y values, we go from 0 to pi over 2. So for our y's now, we go from 0 to pi over 2. And that means if I now put this in an integrand, who's going to be the inside right now? Who's going to be the inside of those two? I want to ask Olivia again. What do you think, Olivia? Which one of these two is going to be the inside one and why? So the one that has to happen first. Remember my tip. Which one has to happen first? The one with a number, the one with a variable? I don't know if you're talking, you're muted. I'm not sure. If you're not.
Okay, yeah, no, that's correct. Sorry, yeah, I was saying from a 0 to y because you have to have the variables inside and the constants on the outside.
All right, so we got 0 to y and then 0 pi over 2, and we've switched the order. Let's see if this actually helps at all. So we got here cos y, okay, over y, but you're doing first the dx integral and then the dy integral. So let's see, did all of our hard work pay off? So if you do the first integral here, okay, you just obtain an x, right? So you get cos y over y, and then you obtain an x, right, that you're evaluating between 0 and y. That's what's going on. I'm just going to write the bounds in red so you can tell apart. Do you see what happens? Can your eye pick up why this actually is better? Because now this x is going to evaluate just to a y. And when it does, it literally will cancel this guy right there. And then you can very easily do the integral now with respect to y. Do you see how we dumbed it down to a cosine integral? That's the beauty about, again, shuffling the order. And over here, this is simply, again, it came from a sine. We're evaluating it again from 0 to pi over 2. Sine of pi over 2, 1. Sine of 0, 0. So you get 1. That's it. A simple shuffling. I don't know if we should call this topic here shuffling, but that's what this problem was about. Shuffle the actual bounds. So I'll name them because, again, we're doing integration techniques, and this is one of them that I thought you need to see. Shuffling bounds, okay? That's definitely one you need to see, to be aware of. Tell me again if you understand what we did. We switched the direction that we are integrating. Instead of going upwards, we went rightwards. And doing so, we were able to get rid of that y that was annoying and then do the integral with respect to y, right? And it was so much simpler that way. But in order to transform, you need to have a plot of the actual integration itself. You need to know where you're integrating so you're able to change the bounds, right? If you didn't know this plot, you can't make the translation, right? So make it a habit to plot the actual integrand for these functions. The function itself is irrelevant, right? Whatever I'm integrating here, like whatever the f of x, y is, who cares? Like this is the least of your concern right now. The big concern in 119 is to actually understand what the integrand looks like. You will have noticed because you have like intersecting planes, I don't know, like solids that are intersecting. You got to picture what the integrand is going to look like. And that's the hard part. not the function. Function, who cares? Could be anything that's under the integral sign. So that's my first example. Hopefully no confusion yet, hopefully. We're not gonna see, I don't think we're gonna see another one of these cases pop up. Okay, if everybody's good, I'm gonna continue the meat grinder here. So next one, look at the next one. They don't even tell you what the bounds are. They just say, do this along the real Cartesian plane. That's what you have to do. Now, we're taking EC 106, okay? I want to ask Grace, what is dA in a Cartesian plane? Because you're taking EC 106, so.
dx dy.
That's what we're doing, basically. And so it says, we have to be really careful. The region is the first quadrant enclosed by these functions. So again, they kind of tell you what you're going to be integrating this, like the space that you're going to be integrating this function in. So we're going to go again and draw the bounds, okay? I'm going to draw the bounds over here. So that is a parabola, okay? So we're going to go ahead and draw it in. There we go. I'm not going to do the other piece because that's not in the first quadrant. Y equals 4 is a line that is horizontal, let's say here. Okay, that's y equals 4. And so again, this is your y equals x squared. And then you have x equals 0, which is really just the y-axis, right? Like this guy over here. All right, so you can see the space forming that you're going to have to do here. That's like your x equals 0. Okay, so your integration space is, again, this bit over here. That's where your function is going to be. That's where you're going to have to integrate. And you have a choice if you're going to do it along the x or along the y again. So before we do anything, you're going to need these points. Okay, you're going to need these points. They're going to be helpful to define the end of the integration, right? So I want to ask Leah, how do I get this point, Leah? I'm just curious. Like, I want to get the x and y value there. I kind of have the y.
Oh, sorry. If
Yep.
you like find the intersection, so if you equate the two equations.
Okay, so for A, we're going to do over here, you know, x squared equals 4. So obviously here, this has 2 roots, but I'm only going to keep the positive one, right? Like the negative one is, you know, but yeah, that's what we have over there. The negative one is, of course, for the other side because they intersect again on this side, right? So that's why I ignore it. Okay, so that's point A. Can Grace tell me what point B is over here? Like, how can I write point B now?
B would be at x equals 0, y equals 4.
Okay, so x equals 2 here and y equals 4. All right, we have the B point. Okay, and C is very easy, Grace. It would be
0, 0.
Okay, so we got these guys down and we need them. If we need them, we'll see when we will use them, but it's good to know. Now, it's your choice which direction you're going to start integrating this. It honestly is. In my eye, I don't know, like immediately when I see the straight bounds, I like them to be the constants, the outside integral. So what I'm going to do instead, I don't know, I like this way, okay? Not to say that the other way is wrong. I don't know. This is kind of attracting me right now. I don't know why. If we're doing it, since we're doing it in the x direction, this parabola has to be defined in terms of x right now. And there it is. That's the positive branch. The negative branch would have been over here, the negative square root of y. So there we go. Okay. And that means that we are taking our integrand Let's try Olivia again. Olivia, what are your X's right now? Let me get Kelly back in because she just dropped. I think she's just at home right now. Okay, I'll just wait 1 second here to get her back. And my question to you, Olivia, is if I'm doing the integral starting with the X, where am I starting? Who's stopping me?
You're going from 0 to y.
Exactly, from 0 to root y. And then in the X direction, what do you see the whole integration span? Like now we got our y, okay? Like, sorry, we got our X done. It's done. We know right now what our X is gonna do. But how much y is the whole integration spanning right now? That's the next question you're asking yourself.
From 0 to 4.
Exactly. That's the easy bit once you have everything above. There you go. So Olivia has put us in for like the solution right now. Straightforward for the solution. So the integral is going to be, again, the inside bit will be the y, right? So 0 to root y has to happen first. And that is that dx, right? That happens first. Then we're going to do the 0 to 4 dy. And then the function, again, irrelevant. Whatever the function is, we're going to integrate it. It is this bad boy, okay? Let me just copy it without the dA. Okay. So here it is, right? Here it is. And we're first doing, as you can see, the x. Now, if you went the y way, would it be any different? You know what? I don't know. Like you could encounter difficulties. Like one approach might be slightly easier or harder than the other one. There are times where like going like this one that we just did. There are times where going this way just doesn't work, right? And you have to change, right? So usually though, girls, both of them work with varying degrees of difficulty. That's the problem. Like personally, I can't guess. Like I have to try them and see what happens from each one. Maybe I get stuck on the yellow one. Maybe I get stuck on the blue one. Maybe the yellow one's 5 steps shorter than the blue one. I don't know from the get-go. I don't think any mathematician can tell you, unless they literally breathe integrals, which one will be the easier approach or the possible one. You literally do it, and when you run into problems, you try the other way. Literally, it's like going one path, and you're like, it doesn't work, so I'll switch directions, and then you do the other way. So that's what I have to say from my perspective. Maybe a mathematician would have more on that, but that's what I believe. Like you have to try it. And it looks like this is going to be good for us, actually. Let me see again what the function is. Yeah, 1 plus y squared there. It looks like this will be okay. Just trust me. I can see something building up here. So I go ahead and I do the x integral first, which means, again, I leave the y one untouched. And we basically have this right now, like the y is untouched. Kelly, I hope you can talk now. Tell me if you can talk.
Yeah.
Okay. What I want from you is just to tell me what this will yield really quickly.
X squared over 2.
X squared over 2. And remember, we're evaluating this bad boy from 0 to root y. Okay. So you can see what will happen. We'll pull outside of 1/2. The rest of it here stays the same, right? Maybe I should just copy this because it's going to be, yeah, it's going to be the same here. Okay, let me turn off the auto sync really quickly. And we have square root of y squared, which is just y, and then minus 0. So this literally just yields you y. You still have the integral with respect to y, right, to do. So you see this? Okay, I want to ask Natalie. I haven't asked Natalie anything. Natalie, what integration technique comes to mind when you see this integral here? What integration technique would cross your mind out of all of them? See what you say. What do we think? By parts. And the parts would be y in the square root. Usually when you see the 1 plus y squared here in the denominator, that's a trigger for trig substitution. No pun intended. Okay? Usually like this it kind of screams like put a trig function in here, right? Because of the identities. But I digress that you can do it even more simply by just observing a little bit. I just want to tell you that right now, if you substituted, like if you took the derivative of this, you're going to get 2y. And you have y in the numerator. What am I suggesting, Natalie? What kind of method instead? Can you see it? So the derivative of 1 plus y squared is in the numerator right now. Not sure? Don't worry. You sub. If you tried here, this bad boy, right? And you go ahead and take the derivative with respect to y, you just get 2y. And so dy is just du over 2y. When you put these things in right now, should we change the bounds? Maybe we should as well. So if y goes to 0, u here goes to 1. And if y goes to 4, u will go to 17. Fair enough. So you change the bounds and you plug it all in. We're going from 1 to 17 in the u world now. All right. And then we have y. The dy we said is du over here over 2y. And so that's why I said this is good because they vanish. And then the denominator is just u to the 1/2. That is all that has remained. So you get overall, as you can see, just 1/4 the integral. I'm going to assign the integral to Olivia, so start thinking about it. So you get the integral here of just u to the negative 1/2 du. What is this? What do we have? Where did this come from? Again, microphone, Olivia. I don't know if you're talking. I'm just checking.
Yeah, right now I'm just quickly doing the integral. I usually do them on paper.
Okay.
So I keep mixing up like I keep having issues, weirdly enough, with doing integration with power rule, and I feel like I really should not be having a difficult time with it.
I know why, because you're mixing it with differentiation 100% of the time.
Yeah.
Yeah, well, when you're undoing this, you're asking yourself right now, what should I take the derivative of to get u to the negative 1/2? And you guess, initially you guess. You're like, okay, what if I had instead like this guy, right? Because if I take his derivative right now, I'm going to get u to the negative 1/2, but I will also get this annoying factor of 1/2, right?
Oh, okay, so you multiply it by 2.
Exactly, and that's how you get the antiderivative.
Okay. So 2u to the 1 over 2.
Exactly. So that's how I like to, show it to students. I always try to guess what's in this box. I would guess if I were you first, and then I would just see if I take the derivative, do I get the right-hand side? Yes or no? If yes, that's my integral. It's just an easier way of, making this a procedural approach. Okay. I'm too bored to evaluate this. Let's just move on. Okay. I mean, I'll get the number for you later, but we have so much to do that I don't want to be playing with numbers. I want to be playing with this stuff, right? So, it's just, you get the constant now. Big deal. So that's that one. And we have a third one coming in. Again, very good integrals, all of them. Look at this one. It says we're going to do the integral of 2xy squared dA. And again, R is the right half of the unit circle. Okay. They give you a hint. I wouldn't give you the hint if it was my tutorial because I want you to grind. They give you a hint to write it in 3 ways. One in Cartesian, then flip the Cartesian order, and then try it in polar coordinates as well. And this is a hint for our next method, which is change of variables, right? This is what's leading us, what we're going to do next. So, okay, we have this. Right now, if I was to do, if I was to understand the integrand, again, that's my goal. What is the integrand looking like? It says the right half of a unit circle. What's the equation of a unit circle, Grace?
X squared plus y squared equals 1.
Okay, so I can go and isolate this right now, either way I desire, depending on what way I'm going to do the integral, right? So I can go ahead and isolate it for x right now, giving me again plus or minus root 1 minus y squared. Or I can isolate it here in terms of y and get the equivalent, but with x, right? Now, which one is defining the right half of the unit circle? We'll have to think a little bit about that. I don't want to use Desmos. You don't have Desmos access on your exam, right? We want to do better than that. So here's the circle, okay? Here's the circle. And right now, 1/2 of it, like this half, is going to be one of these two functions, okay? We've got to figure out if it's the negative or the positive one. I think the answer is obvious, but I mean, we can try and see if it makes sense. So, if, for example, right now you chose the negative one, the negative branch, right? And we put in some value of y. Let's say we put in here like 0.5. You would get 1 minus 0.5 squared, right? And that's going to get you a positive. The square root's going to be positive, okay? So if I chose the negative function, I would get negative root 5 right now for my, or negative root something for my input. Again, try. If you're unconvinced, try a value. Try a point, okay? Try a point. So I go, okay, I'll try here. I'll try like y equals to 0.5, okay? I don't know. I honestly, it doesn't matter, right? Y equals to 0.5. I expect, okay? I want x to be greater than 0, okay? So you try that, and you go and take a look right now, and you do the x. If you pick the positive one, right, you get here 1 minus 0.5 squared, and obviously you get a positive number. But if you try the negative branch, I know it seems silly that I'm doing this, but trust me, you get a negative number. So obviously you want x to be greater than 0 because you're doing this part of the circle, right? You're doing the x greater than 0. So it would have to be, by force, this one right now. You see, and that's how I pick which branch is the correct one. Now, what if I was doing it, though, in the x direction, the integration, right? So what if I was doing the other one over here and I had to choose that? Wait, I accidentally, okay, one sec. So I did this one, all right? That's good. And now we're trying, yeah, for the y version. Okay, so we're gonna try an x now. Okay, these guys now, what did they describe? These guys, let's think about this for a second. If this describes, I have to be careful. Give me a sec here to picture this. this function describes, if we pick the positive part, it describes this half and the other one describes that half. Okay, I got it. I'll explain what I was doing in my head because circles are a little weird with their square roots. So basically, if you work in the X world right now, okay, and I'll show you two plots again. I'll put a plot on each one of these sides so you understand what the heck is going on. So if you work in the X world right now, this function describes, it splits the circle like this. That's what I was thinking in my mind. How does it split the circle? It splits the circle, one second. It splits the circle like this actually, excuse me. So what we were trying to prove is which piece is the negative one, which piece is the positive one, right? That's what we care about. So we try to point, and if I want to be at the right, it says here, the first quadrant, or rather, hold on, the right half of the unit circle, the right half of the unit circle. So this bit, right? We want this bit. So we want this bit, all right? We want this guy. We got to be careful because that part, we proved the positive part has an x greater than 0. So I need the branch that will give me positive x's right now for any y input. And that was this one. So the right one has to be the positive branch right now. I know it makes sense, but we proved it as well. So that's the positive one, and that's the negative one. And this always confuses even me, when I'm doing it. That's why I stopped to think about it before I screw it up. So that's x equals negative 1 minus y squared, right? And that's the one that's positive. I hope that is okay with you. And now I do the same thing on the other one, but the other one splits the circle right now this way. You can see the difference. It's going to split it this way. Whoops. You see? And then you're wondering which one's which again. Who's the positive, who's the negative, right? Okay, well, again, try a point. Try a point. Let me try x here equals 2.5 again. If we want to be here, right, we want our y value for this part to be positive, right? If y needs to be greater than 0, and I try this point, see what value it gets me right now for each of the branches. I think it's obvious to see what's going to happen here again. Okay, so I try the branches, and then I get, again, a positive here and a negative here. What does this mean? What does this mean? This means that the positive y's right now happened, okay, at the positive branch, which means, again, this guy here needs to be square root 1 minus x squared, and the bottom one needs to be the other one. Okay. All right. There you go. So this is useful. The integration, again, needs to happen. They told us what we need to consider. I hope we were reading. They told us, right, what we need to do. And so now it's our choice which way we're going to go, right? Now, what I want over here, this is not very important. It's just for you to figure out which function is where. So I'm not going to include it in your answer. It's just trial and error to see, again, which was the positive branch and the negative. Now what I'm going to do here, again, someone's going to help me out. I'm a very forgetful man. I don't know what to do. So I want Olivia to bother you again. and tell me if I went right now this way to do the integration, because that's the x world. You see my functions are in terms of x. So I'm ready to go in the horizontal direction and do the integral right now. Where would I start in my x and who would stop me?
So you'd have x going from 0 to 1 minus y squared. And if you're integrating like the entire area, wouldn't you also have to add like 1 going from 0 to the negative 1?
You're so close for that one. But when you're done this right now, you answer me the first part. When you're done this, what you're thinking to answer about the y bounds is how much y does all of this situation span right now? How much y does it span?
From it would be like the diameter of it.
So what y points are we talking about?
Just trying to figure it out.
Think about it. They're numbers.
Let me just rearrange for then.
So you see the rest of you see again, we're asking the whole integration that Olivia is doing right now like this.
Oh,
How much
negative
y?
1, it's a unit circle.
Can you repeat that?
Going from negative to positive 1, it's a unit
Yes.
circle.
Yep. That's it. Follow her lead. Grace. Okay? Follow her lead, but we're going to do this way right now. So what's going on here? I'm going to ask you, because we're going in the y direction now, we have to do the y first over here. Where are we going from, again, in the y and 2?
Y goes from negative 1 to 1.
So Grace, 1 second. You see where the arrows start? They all spawn on the blue curve, right?
Yeah.
So that has to be who bounds our y right now from the bottom.
Mm-hmm.
And then they end all the way to the red curve up here. You see that?
Yeah.
So that has to be also who bounces at the top in terms of y. Do you see what I need to write there?
So y goes from negative root 1 minus x squared to root 1 minus x squared.
Exactly. But now I will ask you, following again Olivia, how much x did this take?
Goes from 0 to 1.
You see how different the bounds are? They don't even correspond. Like, you see, this doesn't even correspond with this at all. Okay, well, we're gonna do the change of variables too. It's just that this thing here again, it's interesting. Okay, so the integral now then, one way we can write it, and another one we can write it here. We have two of the answers, not the third one yet, but two ways here that we can write these is the inner one always being the variable one, remember. So we're going from 0 to root 1 minus y squared, and then from negative 1 to 1. And the order is, the first is the x one and then the y one. We've solved that one. Then the other one again, doing the variables first, we're going from negative 1 minus x squared to positive 1 minus x squared. That's the first one, and it's the y one. And then we go from 0 to 1, said Grace, for the x. And there you have it, nice and beautifully laid out. So of course, I'm going to try and do this in polars as well for you, but let's see at least how these would play out. The function's this, okay? So again, the function, nobody cares really. We almost ignore the function during this process. Okay, so there it comes. I don't know, I'll pick the left one to do first. Nobody again cares. So we're going from negative 1 to 1. Again, you have 2xy squared. If you do the integral right now for x, the 2 will come outside. You have the y squared remaining. X will go to x squared over 2. And you're evaluating this from 0 to square root 1 minus y squared. So you go ahead and take the integral, I guess. These twos cancel. What do you have left? You got left y squared, and then your multiply this here will accept this. So you square the square root, basically. 1 minus y squared. You don't have anything from the 0 coming in, so I ignore that. And then you have dy remaining. And the dy again takes you from -1 to 1. So you go ahead and try to pull this off. This is just a polynomial. We can do this in one shot. I'm not really going to mess around. Y squared, the integral is y cubed over 3. And then y to the 4th, the integral is y fifth over 5. This goes from -1 to 1. Okay? And that's the integral. Like, you just evaluate this right now and you're done. So that's that. What if you did it this way? Well, if you did it this way, let's see what we have going. The 2 comes out. We're doing the y integral first. So the y here will be y cubed over 3, and it's being evaluated between these disgusting functions. So maybe this is not the best way to go. I don't know. Look at it, right? Maybe if you got this, you should sit for a second and say, George said, maybe I should switch. You know, sometimes maybe it's worth switching. Because now, okay, I can keep on plowing through this, but look what I have to do. I have to do right now x times, I'm going to distribute the bounds immediately. I have to do x times 1 minus x squared to the 3 halves minus x times 1. I have to be really careful here because this is even. I forgot. This is actually even, girls. 1 second. That's good. That's an improvement. I have the 2/3 outside. I'm going to do it in 2 steps to show you. The integral is still here from 0 to 1. And then you plug in the bounds and you realize, well, this thing, if I raise it right now to the 3 halves, to the 3rd power, becomes 3 halves. And then I have minus, right? Minus. I got to be careful here. 1 minus x squared, 1/2 to the 3rd power. So what I'm trying to say is these are actually just going to add together right now to give you 2. Literally, you can see that the positives cancel here. This negative doesn't get killed by the 3rd power, right? So it stays and it becomes a positive with this, and these add together to give you 2 factors of the same thing. That's what I was trying to say. So overall, you get 2x here times this guy. That's what remains. And I don't know about you. I mean, you can do this. I don't want to do this. Please don't make me do this. You know, I don't want to. What I would do, use some. Okay, I'd go like this. I'd take the derivative. I notice the derivative is sitting outside right now, but yeah, I would get this minus 2x for that. I'd replace the dx with du over, or negative du over 2x. Here they come. This goes here. That goes here. So in the next step, I'd have 2/3 integral from 0 to 1. Then we go 2x u to the 3 halves negative du over 2x, because we replaced that. And of course, these go away as planned. And we go ahead and try to integrate this now. Minus 2/3. Again, Olivia, you see here, I'm looking for a function that will give me u to the 3 halves. When I differentiate it, my guess is 5 halves. But when I differentiate this, it becomes u to the 3 halves, but the 5 halves stay around. So I got to multiply this by 2/5 to get rid of that. That's my thinking, right? And
Yeah,
so
that makes sense.
You see how quickly you can get it once you trial and error? You just don't even have to think about it. So you go 2/5, u to the 5/2 is what remains, and our bounds again are from 0 to 1. So you can be my guest and evaluate that. It will give you exactly, if I did it right, of course, it will give you exactly what the other one will over there. I'm a little worried about the negative though. Let me just check. I'm a little worried about the negative, but maybe this here will give you a -2. I'm just not too sure. We'll have to try and see. I'm a little worried about that negative. That's all. Yeah, well, but the derivative is -2x, right? When I plug it in, and I didn't make a mistake here, did I? No, I don't see one. These will be proof checked by me later because I've solved them in my own notebook. So I'll proof check them in order, if by accident, let's say I put the bounds inverted here, I will correct that for you, right? And I will mention it in the recording that we messed up, but I don't feel like I've messed up. I can check.
Wait, sorry, how do you get the 2x?
This one.
Yeah.
So I said when you plug the bounds in, the y cubed right now, you get 1 minus x squared to the 3/2 power, right? But these add up. Like when you add them right now, like when you do the integrand, they will add up. You get 2 of these factors, basically, when you do the algebra. And the 2 came from there. It's like having, again, a situation where I have 1 minus -1 here, Kelly, and this adds to 2. That's what's happened. But these -1s are multiplying 1 minus x squared to the 3/2. So the 2 comes there. It's like having a situation like this in the evaluation of the integrand. That's why.
Okay, thank you.
But I have to kind of speed run them through. Sometimes I avoid giving the full picture. But if it causes confusion, let me know. Okay. So I think we're good. And then the last bit is saying, why don't you try this in polar coordinates? Oh boy, joy. So, okay, you've got these 2 methods. And so we want to try this in polar coordinates right now. And we know what the bound looks like, which is a good place to start. Okay, we know what the integrand looks like. And I just gotta figure out like how this thing will look like in polars right now. And I'm pretty sure you can, again, EC 106 should have prepared you for this. Okay, the grind that we're doing there. You look at this right now, it's like, reminds you of the disk problem or any disk problem that we do in EC 106. And I go, what's the coordinate system we should use? And you're all yelling, polars. Fine, I go, okay. Remember how I told you in EC 106, maybe, just maybe, you should write down what your interested shape looks like as a bound of your coordinates. So for example, here, let me ask, I think I should ask this one to Olivia. Let me ask Olivia this, okay? Look at your R vector right now. This is your R vector in polars, right? I just want you to tell me right now what you think this R vector will do. We're going to do the integral in little rings, right? We're going to start like this, going to go around like this, and we're going to go around like this, and we're going to go around like this. Just follow my arrow here and tell me what values of R do you see it visit right now? What values of R is it going to span until it gets to the very end here?
It'd be going from 0 to like a little r.
That's what we write in EC, but the little r here is what? It's a unit circle.
Oh, 1. So 0.
1. So our shape here, again, this is a good way to write its R values. And then do you see our phi, what it will vary from and to here, Olivia? Again, phi is the angle with respect to the x-axis. Do you see what it would go to?
Yep. Negative pi over 2 to pi over 2.
Beautiful. There we go. That is your shape. That is your integrand, basically in polar coordinates. Now, can I ask Grace a more difficult question? What is this in polars? What is this guy? Whoops.
RD phi.
So that's the R d phi, and that's the dr side. So all together, okay, is r d phi. Okay, so you have the integral now written in a third way, okay, third way, where it's going. As you can see, it doesn't matter the order that we do it now because there's no variables in the bounds, but we're gonna, I don't know, do it whatever way you want. I'm gonna do the R first and then the phi. So I'm gonna go like this, and that's gonna be dr d phi. So you go, okay, but George, this is still 2xy. How do we integrate it with respect to r and phi? Can I ask all 5 of you, what do you think I should do here? Because this, you might not know. Just want to see who knows what I should do here next.
Don't you convert like the x to cos phi and then the sine or the y to sine phi?
Okay, so x, we know polar coordinates look like this, right? I forgot the RD. Oh my God, I almost forgot here. I have to be super careful. This dA is what Grace said. So I almost made a mistake here. Okay, so our polar coordinates again, this is how they look like. And Grace told me what the area element is going to be. So we're just combining all of our forces here to write the integral now. So it's ready. Minus pi over 2 to pi over 2, 0 to 1. That was the hard part, I believe. And then the 2 comes outside. You have x and y, which is r cos phi, r sine phi. You see them right there. And then you have dA, which is r dr d phi. Voila. So,
Wait, I think you wrote y equals our cosine phi.
oh my God, sorry. Thank you for catching that. I need to slow down a bit, even though we're in a rush. There we go. Beautiful. So we have the,
How did it get to the 2xy with those bounds?
which one, point me, Kelly?
Like how did the original equation go to 2xy?
Was it different? Oh, it was, okay. Sorry. There we go. Again, thank you for catching that one. It just means that we have to square this one, right? So we have, let's slow it down a bit. We have the integral here, still the same, bounds and everything. But the inside here is becoming, now we can split this integral because really, if there's no variable right now, we can split this up at this point. So I'll have a total of, that's r squared here, r cubed, r to the 4th. Well, there's the r to the 4th, dr. And then my phi integral, I have cos phi, sine phi going on over here, d phi. And the sine phi squared. Fair enough. So I work on them simultaneously, right, to get rid of them. The R1, I just noticed what I've done here. Don't worry. The R1 is going to be very easy to solve. The phi one needs a little more work. Okay. So we got 2r5 over 5 evaluated from 0 to 1. The other one here, I've made a video, Olivia, about this. I'm just saying, okay, shameless. I made a video about this, and what we want to be doing here, okay, this is already solvable, by the way. This is a class of integrals of its own. Which class of integrals is this? Let me explain. If you take the derivative right now of any power of sine, can can Leah tell me right now, if I was to take the derivative of sine x to the nth power, what would I get here, Leah, on the other side? Just the derivative of this. I wanted Leah to tell me, but
Sine 2x.
this is a constant. Remember your chain rule. It has to come to the front. Give it a try. So the constant here has to come to the front. So the first thing you're going to write down, Leah, is
N cos x.
what happens to
Sine,
this? Yeah.
sine n minus 1x.
Ah, okay. All right. All right. So what if I told you right now, that this here, okay, I want you to see this. What if I told you right now, I'm just going to rearrange this one sec, just to prove my point. Sine n minus 1 cos x is equal to 1 over n times this derivative. And again, I can take this because it's a constant. I can take it in here, right? Like it doesn't really influence anything. So, what if I had that this is equal to 2 right now? What if I had that this is equal to 2 right now? What would happen? What is its antiderivative? If this is 2 right now, what's the other side? What's happening inside the bracket? Still Leah. So if this is 2 right now, okay, n has to be what? N has to be what here?
3.
Right, okay. So what's happening in here? Now you can find it very quickly.
So, 3 sine 2, like sine squared.
You're
Cosine.
close. You said n is going to be 3 though. So in total in here we have,
Oh, sine 3x over 3.
yeah, that's the antiderivative. Okay, no substitution, no games. That's the antiderivative. You found it. How cool is that, right? This is a class of integrals again that I talk in a video that I've made, right? And you can think of them this way. Whenever you see a cosine multiplying a sine of any power, it has come from some kind of sine and vice versa. So no substitution required here because we're bosses, okay? We know what's up. And we just do this. No substitution required. Okay? I'm not going to carry this more forward. Again, it's just numbers now. I did the integral. It's over. So all of these three, if I've done them correctly, all of these three methods will give you the same number. All of them. Okay? I will check them after to make sure, but all of them should yield you the same number. Okay? Every single one. Okay, I'm just going to deposit this here. And that's that. That's the whole question. So this is a good grind, on integration, finding your bounds and all that, because I'm sure it sucks. And then we have this guy, okay, where we have to change variables here. Okay, we have to do something to figure out the volume of this thing. This one over here is similar. We'll have to change variables. I just want to see how many examples I have, because I've lined up quite a few and I want to make sure I'm on time. And I want to show you this stuff too later. So, okay, we have time. What I want to do though I hope it's okay. I'm just gonna ask for a quick washroom break. Couple minutes. And it's your chance again, clean your mind for a sec. I think the next logical one to go to is this, okay? From where we are. And then we'll build up to triple integrals, and then we'll do change of variables, and we'll talk about the Jacobian. That's my biggest, again, what I want to show you tonight. It's the burning topic in my head. So watch this for a sec, start thinking about what we're gonna do. It's a volume integral. I've given you the cheat over here in a way. So we're gonna have to basically integrate this, okay? So let's take a couple minutes of a washroom break and be right back. Recording is paused. So let's roll. Inverted cone. I don't really need to draw the cone right now because, I mean, they've given me the equation and they're asking me for the volume of this, right? So it says use a double integral in polar coordinates to calculate its volume. I can give you a quick, interpretation here of the cone itself. Like that. And again, we're going to try and figure out what this cone's volume is going to be. Now, we can get it by, of course, integrating the level curves that we have in hand. But a more clever way is if we have the actual function of the cone, all I have to do is literally just integrate it with respect to the area element on those level curves. Like, I'm not really concerned about anything else. It's just a regular integral in my eyes. So, we have to talk about the bounds though. Again, those pesky bounds. So the cone's like this, right? And its level curves again are perfect circles, right? Like if you look down, project yourself like this, those level curves are all perfect circles. And what I've done is I've laid them out for you in a projection over here, like the XY plane, right? That's really what I've done. In this plot, maybe this would be the Y and maybe this would be the X direction right now, right? And this would be the Z. Just saying, right? Like that's how it might be. I don't know how you want to align your axes, but I guess a way is what I'm drawing here for you. So again, what you're seeing over here is the projection right now, right? Onto the XY plane. And we see a bunch of level curves, okay? How do I know bounds, right? We want to find the volume above the XY plane here. So how do I know the bounds that I'm going to have to go to? I think you can tell. I think. It says above the XY plane. Above the XY plane. Actually, if it's an inverted cone, my bad. If it's an inverted cone, yeah, it's like this, right? Not this way. That's a normal cone. But I didn't notice that. So let me just do that. Flip vertically, sorry. And I'm gonna put, of course, what I'm gonna do is I'm gonna put this here. I'm gonna do that because it's an inverted cone, right? So also I made it a little messed up here. That's good, that's all right. So let's put our XY plane. I'm just deciding where to put the XY plane right now based on the equation. It should be lower, definitely. It should be at the base of the cone, actually. That's what I'm noticing. So I will have this moved here. Just line it right up. And then I'm going to have to move the Z-axis like this. And then the cone will come and be on top like that. Okay, maybe make it a little smaller. And there we go. So what is the highest value that I reach here for my Z? We need to ask ourselves, right? And what's the lowest value? I'm just taking a look. As X and Y are growing, Z is becoming smaller. Yeah, so this is again an invert. I've drawn it correctly. So as X and Y, right, go up, you can see that we're subtracting bigger and bigger values. So that means Z is going down. So again, one more time. One more time. If we move this way in our Z direction, our X and Y should grow. You see, that's what I'm telling you. So I'm sure now that I've drawn it the right direction. That's how I justify it. Fine. What is the maximum value that Z can be? Grace, what do you think?
A 10.
Uh-huh. What is the minimum value that it can be?
0.
Okay. Now hold on, this gets interesting. So she found the maximum Z and minimum Z that we can have. If you haven't noticed, again, we're gonna have to deduce what X and Y need to be. That's the problem here, right? We need to deduce what this means for our Y and X. So how do I do that? Well, we got a function here for Z, right? You got a function. And so using this function and the values that Grace just told me, okay, I can go and see what happens to my friends X and Y. Okay, so I'm going to go this way, I guess, to find the maximum. And you can see what's going on here, right? So we got over here this. So this means basically, if these drop out, this means again that this yields nothing. Makes sense. Okay, that's one of the level curves that we get. Hold your horses. I know, like this makes not a lot of sense right now. Hold your horses. And then we go and do the other one, right? And I'm like, okay, 0 is equal to 10 minus root x squared plus y squared. So that means that square root of x squared plus y squared is equal to 10. If I square both sides right now, if I square both sides, what do I get? Well, here I get this. Actually, I'm not going to square. I changed my mind. What I'm going to do is, girls, I really don't think we should be in Cartesians. Look at the cone. Anything that has circular nature to it, I don't think you want to work in Cartesians with it because it will become disgusting. Now, what you could do, obviously from here, what you could do is you could solve for what y is in terms of x, right? And find, again, bounds between, we can write the integral in terms of dx and dy or dy dx. I think you can be more clever than that, okay? Because the level curves are circular. Why are you trying to do them in Cartesians, right? When you have polar coordinates as your friend. So what am I saying here? You got over here something and something else. And if you have a keen eye, maybe I'll ask here Natalie now. I haven't participated with Natalie. Maybe if you have a keen eye, you could tell me what this is in polar coordinates right now. P? What's P? Rho, you meant? I'm not sure. Can you repeat that, Natalie? Like, what's P? Yeah, rho. Okay. So it is the R variable. That's it. R squared right here. And because it's getting square rooted, what you have right here really is R. Ah, okay. You have R going from 0 to 10. Ooh, okay. And then if someone was to ask you what the phi is doing, well, I think you can tell now. So the R again, we're doing the integral I'm going to show you just to make sure you understand what the heck's going on. We're doing the integral like this. So the R, let me just go down here. Pick like one of these disks, okay? One of these disks right now. And what the R is doing right now, which is represented by my yellow arrow, you know, we started at 0 always. And then what it does, okay, it's going to spin around, create a little disk, then it's going to grow by a unit. Then it's going to spin around, do that disk, and then it's going to grow by another unit, right? And then it's going to eventually reach the slant of the cone here, where it's going to do its last loop around. You see? And that's what it does. Literally, that's what it does. And it repeats that until it spans the entire cone. So we're saying over here that you're basically doing spinaroos around from R equals 0 to R equals 10. And your phi, of course, if you're doing spinaroos, you're completing full circles, that's from 0 to 2 pi. So that's what's up. Wow, you got bounds. You see? And another way you can see this is from the level curves. That's why I had the level curves here. Another way you can see this, I have to be really careful though with this. Hold on, let me be really careful. I don't mess this up. Okay, so for the level curves, I've drawn them over here. They're circles. Ironically, okay, the 10th level curve is the very top one because that's where the cone, again, is opening up from, and then like you come down. So essentially these level curves, I haven't drawn them all. Now I realize why this is bad. I haven't drawn them all right now. I haven't drawn all the level curves, but I think you can see if I do 0 here, how do you draw level curves? You just set the Z here to some value K that you decide what it will be. So right now, if I choose this value to be, let's say the K equals 0 level curve, right? What I'm going to get is a, again, imagine that this is just R right now, okay? What I'm going to get is R equals 10. You see? So the 0th level curve is the outermost one, okay? I haven't drawn 10 circles here. I could, if you want me to. 1, 2, 3, 4, 5. You get the drill, right? 6, 7, 8, 9, 10. I'm not going to be able to fit all that on my plot, but this would be the K equals 0 level curve. And then as we move to higher level curves, like K equals 1, look what happens. The 10 now goes on, or sorry, the 1 goes here, the R goes there, right? And we basically have, why don't I do this so I don't confuse you one sec? Replace this with K, replace this with R. The new equation is, if I move the R on that side and the K on this side, the new equation is 10 minus K. That's it. So if K equals 0, R equals 10. If K equals 10, R equals 0. So up here, this guy, this level curve up here, I'm going to indicate it. That is the K equals 10. Okay, because that has no radius. And then the bottom one over here, that's going to be the K equals 10 level curve. Just a little bit of a wait a minute. That's going to be the K equals 0 level curve. Okay, just a little refresher on level curves, right? How we draw them. So again, on the 2D plot, it would be the very inner one that is the K equals 10. And you can see it. It's like an elevation map right now for the cone. Okay, but if we're doing its volume, if we're doing the volume of the cone right now, we got to integrate this entire space. And this space goes clearly, you can see this radius here is 10. It starts from 0, and we're going around in circles of 2 pi to space it all out, right? That justifies the bounds that I told you earlier, but I showed it in a different way. So the integrand again, this is it. That's what we need to span. So to span it, we move r from 0 to 10, and we rotate it from 0 to 2 pi all the time while we're doing so. F of xy gives us the volume of the cone eventually. It's the area of the level curves. Okay, so without further ado then, let's set her up. Okay, so to find the volume, every single time we said we need the function, and we're gonna multiply it with dA in that, in whatever polar coordinate system we're in. We're in polars, and Grace told us what the dA is in polars. She said r dr d phi, and the function for the cone, okay, it's given to you in the beginning. Kind of lost it right now, but it's given. There it is. Okay, right. This is the function. You're gonna say, George, that's in Cartesians. Yeah, I know. Relax, we got it. Right, just like before. You're gonna put it in. You're not done yet. You've done the bounds, you've done the dA element, but you gotta work with this guy too, right? The bounds, once again, for the r integral go from 0 to 10, and for the phi integral go from 0 to 2 pi. Okay, so how do I get rid of the Cartesian nature of this function? Well, we said this is just r. Substitute. You see? So the volume here is 10 minus r dr d phi. Okay, so we're gonna open it up a little bit. What do we get right now? We get 10, I guess here 10, this double integral. I can actually factor the phi integral. Why am I gonna not do that? I can factor the phi integral outside. Like, what are we doing? Just factor it. And then inside, we can do 10 r dr from 0 to 10, and then minus r squared, I'm doing this one right now, r squared dr from 0 to 10. Nice. That looks good to me. So the phi integral here is like 2 pi. And we do the rest of them. So we got 2 pi. Let's see. 10 r squared over 2 minus r cubed over 3. And this is all getting evaluated from 0 to 10. What do we get? Let's check. 2 pi. The prefactor here is 5. Then you get 10 squared from the bound over here, but then I get 0 for the other one. And then the r cubed version, you get the 1/3, and then 10 cubed. And then the 0 again, which I don't count. So in overall, let's see if this makes sense what we're getting. We're getting 500 minus 1,000 divided by 3. That's your volume. Done and done. So yeah, I chose to do it in polars, and that's why the problem is called change of variables, because it's so much easier and I can see the actual integrand. I can see the integrand, you know, bright as day, what it is in polars, but in Cartesians, it sucks, right? That's why we're changing. So my tip again, when should you change? It's circular. It's circular. That's like a trigger that you should be thinking polars or cylindricals if you have a 3D problem. So that's the trigger, right? Circular. It was also circular before on the previous problem here, right? It's also semicircular. That's why this was way easier than these were. So think about that for the future. And that's that. Now, again, I might leave that for you to try. You can see again here that this is low key r squared. Okay. So I'll leave you with that as a hint and you can try it. Okay. So to the more burning problems now. I hate triple integrals, I have to tell you. I personally despise them. And it's because of stuff like this, okay? Like, I hate this stuff, right? I'm not you don't have a graphing calculator all the time in your pocket that can do 3D plots like this, right? So you most of the time you're alone, you have to draw this, and it's not fun. But of course, that's exactly why I stole my own diagram here, right? Because I wasn't gonna redraw the whole thing and spend 20 minutes. I wanted you to just get the plot. So I don't know if we do the cylinder or the cone first. Either one is a very good example. This is hard. So I might not do this one right now, but I want to show you something that you can follow. And this is something that you can follow. So it's a cylinder, the problem here. Here's the equation of the cylinder, I guess, the level. Let me make sure this is okay. Calculate the volume of the region that is bounded by the cylinder, this guy. If you're in 3D, I know what you're thinking. That's a circle. But if you're in 3D, this is actually a cylinder, okay? The planes are x equals 0, z equals 0, and z equals y. And we are on the first octant where x, y, and z are all positive. Okay, so we got to remember x, y, and z are all positive. That's where we're going to be. That's another constraint here. Okay, they even suggest using a plotting program. That's how bad the question is, right? So I know we have a cylinder, and I know there's going to be a bunch of planes intersecting. I think that's what I got from the plotting program. I think that's mine. But anyways, we can visualize it, okay? Thinking about the planes right now. Let's see which one's which over here. We have planes. Let's write our equations down. We have the cylinder. We have x equals 0, y equals 0, and then z equals y. So these are the things that I want us to distribute on this plot right now. Remember, we're trying to still find the integrand. That's the hard part because it's now a 3D region. It's not a flat surface that we did in the first question. It's now a 3D region. So we got to find out what the integrand looks like. Okay, so I want to work here a little bit with, let's try again, Olivia, okay? Obviously here, Olivia, that's the cylinder. But I want you to see and tell me which color corresponds to each plane here that we have left on the right, and try to justify why that is.
Okay. So I'll try and find x equals 0 and y equals 0. So y equals 0 would be the blue one.
All right, 1 second here, because I made a mistake myself doing this right now. So that's the z-axis, that's the y, which means right now the x-axis will be pointing toward our face, okay?
Oh, okay. Yeah. Okay.
Maybe think about the orange one first. What do you notice about the orange one? Which variable is never changing about this orange plane? Like if I extend it right now, which variable is never?
The y value. Oh,
remember this plane is infinite. And I'm just going to do this. This is going to help you a lot. Which variable right now never changes for this plane?
I can't really tell.
Is the y changing? Look at the axis. Look at the axis right now. Look at the y-axis.
Yeah.
Right, because look at us. We're moving, right? We're moving. We can move this way. Is the Z changing?
Yeah, but not the X.
But not the X. So who do you
Yes.
think describes the orange plane?
X equals 0.
Right, because this plane is locked onto the X equals 0 coordinate, right?
Mhm.
That's what's up. So let me put it back in, and that is its equation. With a similar logic, which one do you think is the Y equals 0 right now?
The blue one.
Okay, now I have to fix the coordinates because I'm being a dum-dum here. This one, if this is to make sense, right? We said it's pinned at Y equals 0, right? So that means that I have to be careful about this. Let me look at it. Why did I draw it like this? There has to be a reason. I think I drew it like this because it's very obvious. This one here, the plane that is defined by this, you can see that as Y grows, Z grows. So this is a plane that has basically that is basically a bunch of lines that are sloped at 45 degrees between the Z and Y axis. That's what we're seeing here. This pink one, these are all just lines right now, okay? All just lines that are sloped at 45 degrees between the Z and the Y axis. That's what this defines in 3D. So that's why you see that slanted plane, okay? And I've drawn my coordinates like that, okay? The other one though here, the one that's Y equals 0, actually, let me be a little careful. How would it look like? It would look like, again, we would pin this at Y equals 0. It needs to look like a door, actually. Hold on. This is wrongfully drawn. It needs to look like this. Like a very thin plane. It's going inside and outside the page. And I hope everybody can follow why that is, because if you're at Y equals 0, you need to stay here on the ZX plane. You need to stay here. You can't have extent in the Y, right? You cannot have extent in the Y if you're that plane. So you must cut into the page right now to satisfy this, like that. So that's how your plane looks like, the blue one. Maybe I mistakenly drew it like that on my previous diagram. Maybe I caught a mistake. Who knows? So that's how it looks like, this blue one. Okay, so it's slicing in the page and out of the page. The orange one is flat in our perspective, and the other one is slanted at 45 degrees to the ZY plane, because that's its equation. Now we have a good picture of where the hell we are, right? That's a good picture. Okay, but we still have a little bit more to talk about. The volume that we're trying to find right now, think of this as being the background. Right now, this is behind everybody. The volume that we're trying to find is hidden here. Okay? And they said we are right now in the part of the octant, I guess, because if you have a three-dimensional space, you don't have 4 quadrants. You have an octant, basically. And the part of the octant we're in, I don't know if you can see it. The one where all the values here would be positive, it'd be this guy. There, that's our guy right there. So that defines like the bottom of our integrand, and here is like the space above it right now, right? And it reaches all the way here. So it's a 3D kind of shape that we're trying to model right now, 3D volume. On the shape here, I don't think I could draw. It's inside. It's the volume inside this bit that we're trying to find, if it makes sense. Only in this bit, though. Only in that bit. Not in that bit. Not in that bit. That's not in the first octant, right? Or that bit right there. No. It's right underneath the plane, above this one, and behind that one. And that's the first octant. You see what I'm talking about? So you're trying to find the volume inside this space. Okay, so the perspective, again, you're looking this way, and you're looking this way here to see it again. I hope the pictures match on your brain now, like how they, the perspectives between each other. Okay, so how does this look like from a top view, okay? What if I was looking at it from a top view right now? And that's what I'm trying to draw here. How would it look like from a top view? So again, let's check if I've done it right too, over here. I'm gonna check the top view. So if you look at it from above, you have this to define the circle, right, over here. The blue plane, I have to be careful right now. I've mixed up here the orange plane and the blue plane, so it hasn't been done correctly. So again, how does the blue plane look like right now to me? The blue plane would look like coming in and out of the page. So I've mixed up the colors here. That's all that's happened, really. Yes, I don't know why this happened. I don't know why. But the blue plane, again, when you look at it from above, remember, this has Z extent, so it can come in and out of the page, right? And it also has X extent. So what I'm drawing here is the XY plane. I have to be really careful to be able to cross-correlate here, the plots. So if I'm looking at it from above, yes, that cuts like that. And it can be along the X direction, yes. So actually, the blue plane looks like this from a top view. Okay, much better. I think what happened was when I was drawing this, I mixed up Y and X in my brain when I was trying to do the top view, but that's all right. That's how it looks like though. When you're looking down on this, you can see what I'm talking about. This plane does not extend in the Y at all. You see, I told you it does not extend in the Y at all. And this is evident here because I've squeezed it down. You see, it doesn't have any Y extent at all, but it does extend in the X. It does extend inside and outside the page, we said. So that's what we're drawing over here. Meanwhile, the orange plane, we see that it doesn't extend in the X. You see, it doesn't extend in the X at all. It's pinned at X equals 0, which means it actually looks like this. Interesting. Interesting. And then you have this one that's slanted. How the heck would this one look like over here, right? If you have Z equals Y and you're trying to project right now, you're trying to project this on the actual XY, right? How does this even look like? Well, the projection of this is obviously going to be a line again, right? When I shoot light down, it's going to be a line. But I want you to try to picture it for a second. This plane right now, the pink one, is going to cast a shadow on this region and it's going to fill it up. It's going to cast a shadow. Let's see it from this perspective, okay? So inside here, you see that this plane, when I project from above its position, it's going to cast like a shadow right there. That's what it's going to do, right? It's going to fill that space with its shadow, right? So that's what's happening. So in fact, we are here. That's what's going on. Obviously, the plane casts more shadow, like the shadow of the plane in total is like, as it's going by above, right, over here, it's casting a shadow like this. But obviously, we're interested only in the part that's intersecting between the two planes, the cylinder and itself. So the only part that's intersecting is here, right? Between all four of these objects. And we're interested in this shadow right there. That is how the bottom of your integration part looks like. That's the flat part. Okay? There it is. That's the shadow of the pink plane. I'm just going to draw it in pink. Hard stuff to visualize. But nonetheless, you have an idea right now of what the heck is going on. And by that, I mean, take a look again at how I could do this integral We can try and do it if you want in Cartesians or polars. We're trying to find the volume of this. I would suggest doing immediately, you know, cylindricals, but whatever. If you're trying to find the volume, right? Well, we're trying to integrate the volume element over here. And the volume element in cylindricals, maybe you haven't used it yet, okay? Maybe you haven't used it, but the volume element in cylindricals, I've put it here for your reference, okay? Why is this RD phi? Because there's a bunch of radial vectors that extend like this, and this is d phi right now, right? So this guy right here is this side. You have extent in the z direction, right? A small change up is a small change in the z. And the r here is because, again, that is the r's direction right now. And a small change in that direction is just called dr. So you put it all together to get the volume element, right? You just put it all together. And you might have not worked with this yet in EC 106, but that's the volume element. So you steal that, okay? We know it exists, we steal that. That's what we got to fill in. Okay, we got to fill this guy up. And it's a triple integral, as you can see. Not very fun. Okay, so let's make sure we don't make a single mistake. We now have to put proper bounds for this. We don't have any function that we're integrating. We're not integrating a quantity right now. We're just trying to find the volume, right? So we're just trying to integrate this between the appropriate bounds. That is it. What are the bounds? If we're in cylindricals, maybe we can see. So I would start here very cautiously working my integrand from inside out. Very cautiously, because I can make a mistake here too. Let's say right now, I want to go and fill this space, my 2D space like this. Okay, I want to start and integrate this way. To me right now, this corresponds. Actually, let me think of it a little bit differently, because we said we're going to jump into polars immediately. Okay, if we jump to polars immediately, and I see again how I'm going to do this integration, right? My R vector is going to be doing rings like this. Follow my lead here. It's going to be doing rings like this, right? So I think the very last variable we should define is the phi. I think that should be our constant right now, the phi. And I think you can tell where it goes from and to. Olivia, where does it go from and to, the phi?
0 to 90? Or 0 to pi over 2?
Okay, 0 to pi over 2, and that's going to be my last one. Okay, I want this to be the last one. Okay, so the more difficult stuff comes from realizing how the R needs to be treated and the Z, right? So the Z and the R have some relationship right now, undoubtedly. Okay, there's an intersection happening, and we need to find out what that relationship is. Okay, so that's the challenging part here, to fill these two guys in. But we're almost there. Okay, we have the plot. We can do something about that. Okay, so we're saying the Z here is equal to Y. Z is equal to Y. Can I ask Grace, any idea of what I could do with this information here specifically? Any idea?
Not really.
Okay, don't be scared. Z is a running variable in cylindrical coordinates, all right? What if I told you that this right now is telling you your upper bound? And it says your upper bound is Y. And you know what Y is in cylindrical coordinates. It's the same as it is in polar coordinates, which is, what do you think?
Rho sine theta.
Okay. And if again, this is the guy that stops you here. Hold on. If you're stopping on the XY plane, what is the lowest value of Z you can have? Still Grace.
Z equals 0.
So Grace is telling us right now that this is Z max. And she's telling us that Z min is 0. She got the first bit. And why this needs to go very, very first, I hope you can see why we need to do this as the first integral, like the very, very first one, like dz, r dz, dr d phi. The reason is because this guy right now starts and has an r on its integral. He has an r. We're going from 0 right now to r sine phi. That is the reason. You see how very careful I am to not screw this up, okay? I saw that it contains an r and a phi, so this needs to be the very first one, the very inner one in the triple integral that needs to go first, so that it leads us to r and phi only in the integrand, and then we can continue and do the dr and the d phi. Interesting how this cascade is happening. And then Olivia found the very bottom here, okay? Olivia found, didn't I write this out anywhere? What is wrong with me? So Olivia said the very bottom here is supposed to be the phi, which goes from 0 to pi over 2, it looks like. And then the middle guy is the r. The middle guy is the r right now, which we need to talk about. Where the hell does that go? Let's take a look. R again, I think now you all can tell what I need to do with it, right? R is going from, it's going from 0 to the intersection with this circle. But I'm so lucky here that the circle has a very simple equation in cylindricals. Very simple equation. What is this equation in cylindricals here? Let me just, what is this in cylindricals right now? Grace will be able to catch this.
Rho equals 1. Wait, rho squared equals 1.
Okay. Or r equals 1, because again, r cannot be negative. We can't have a negative r in cylindricals. That doesn't exist. Do you see that? That's jokes, right? Compared to like what it could have been. What if it was, let me tell you what I mean right now to impress you why this is so exciting. You could have had something like this over here, okay? And this could have been, okay? Just to understand why this is so exciting, because that's disgusting, right? Like you would need to go from 0 and your r vector would need to obey, like it would need to follow and trace this function when this would be its outer boundary. And that would be disgusting, right? But you don't have that. You have this, right? You have this, and that's just a constant in the cylindricals. It's just a constant versus the disgusting function I showed you would have had like thetas, r's, who knows in there. It would have been disgusting, right? But no, you go from 0 till the circle that is defined by r equals 1 in our cylindricals. And that's it. You got the full story. How beautiful is that? And now we go in and fill the other bound here for r, and we're ready to roll. Now, again, you can see that I need to follow the order that these are written right now. I cannot do anything. I'm locked, okay? So what I'm going to do here is I have to do the Z integral first, sadly, but it's not that bad. So I have remaining r dr d phi. The Z just pops up here to bring in the r sine phi. That's all it does, really. the Z guy. Okay, sorry about that. There we go. So in the next iteration, we have R squared dr, oh, don't forget the sign, dr d phi. And we're going, now we can split this integral, by the way, because it doesn't have any variables in the bounds, right? So know when you can do that and know when you can't. It doesn't have any variables anymore. This is free. So I'll do the sine integral on its own, and I'll do the R integral on its own, like that. Okay. So if I go ahead and do them, this here, I have to be careful. It came from a negative cosine. I'm going to absorb the negative though, girls, in the bounds. Okay, so I'm going to go from pi over 2 to 0. And then I'm going to, this guy here is obviously r cubed over 3. And I'm going to evaluate him normally. So as I'm going through, I have cos of 0 minus cos pi over 2. And then I guess the 1/3 can be pulled outside of the front. And then you do the r cubed, which just gives you 1. Right? So the total here, cos of 0 is 1, cos pi over 2 is 0, and you remain with 1/3. Whatever the units of your coordinate system are. That's it. We can all agree to hate triple integrals together, but that's it. This is a very complicated intersection, okay? And that's how you would go about it. You need to think very carefully which of the coordinates has a variable dependency when you're making up the integrand. And when we were doing this with Grace, we realized here that the bottom is 0 for the Z, but the plane is what defines the ceiling. And the plane has this equation in Cartesians, which I can switch to cylindricals by just writing what Y is in cylindricals, right? And that involves both R and phi, which makes it necessary to be done first. Like that is the bottom, the very inside of the cascade of how I'm going to write my triple integral. Then the other two, this here, for example, could have had a phi dependency. Like this bound here could have been 5 cos phi, for all I care. And it would be the middle bound now because I have still a phi dependency. And then I would integrate the phi at the very end, which only has a constant dependency, right? That's how I bring my variables as a cascade. So the topmost one in the triple integral usually has both dependencies of the bottom two. You can see the R here and you can see the phi. Typically the middle one would have a phi dependency. It just so happened you're lucky here. I told you, you don't have any of that. And then the bottom one needs to be a constant always, always. And that's the cascade. That's the part that kills students right now, understanding how to put this together. And now you know, at least I hope you know. Okay, so we put it together, the cascade happened beautifully, and we got to the answer of 1/3. Okay, so I love to do this in cylindricals. You could have done in Cartesians. I don't recommend to. You're gonna regret it. Trust me. I can see why, but don't do it in Cartesians. It's like not good. All right. Don't forget. Don't think that I forgot your question, Kelly, about like the one that you sent me on Discord. I have that planned as well to happen eventually, but you know there's so much to do. I really want to show you this one, but this is way easier than the one we did. Trust me, it's just 2 concentric spheres. Way easier than the one we did. Okay, so that's the next one I want to move in as the time passes. And then if we have time, we will do more, but this is burning. This is a burning topic right now. How do you do these substitutions? What the hell is going on, right? Like you want to integrate. It says here, let D be the region in the first quadrant bound by these curves. So one of them is x squared. The other one is 7x squared. And then these are inverted parabolas. You got like two parabolas opening up and two parabolas opening down right now. And this is my poor man's diagram of the situation. So the intersection right now, don't forget we're looking only in the first quadrant. So I'm not considering this intersection here. The only intersection in the first quadrant of all four is right there. And the problem here, let me tell you why the substitution is even needed, because you're gonna be like, what the hell? You know, just integrate this. The problem is the following. Look what happens if I try to define this region if I did not do a substitution, okay? Let's say I'm gonna do what I did in question 1 today, and I decide to go this way. So you can see this is cool as it's happening, but oh my God, the orange curve stops here. I have to switch now because the right bound, right? The right bound now is the red curve. Can you see what I'm talking about? We switched over there. The red curve right now is the right bound. You see that? And that's what's happening. Oh, and it happens again. Look at this. So as I'm going down, over right there. Now the blue curve is on my left side. So I have to switch again. I have to break this down into 3 different integrals. And they're both 2D. You want to do this? I mean, you want to be my guest? I'll pay you. Go ahead. Solve it for me. Do the 3 integrals and I'll pay you to see the solution. Well, it's already bad enough with the functions that you have, but do you see the problem? Olivia, I think again, you're talking, but your mic is muted.
Oh, well, we have to split it up into 3 because that's the only way,
We're smarter than that.
I'm running on no sleep. I'm trying my hard here.
Don't worry. We're smarter than that. We're not going to do 3 integrals, okay? But I'm telling you, if you were to brute force this right now, how it would need to happen, right? You would need to do 3 separate integrals, one having the yellow curve and the orange curve as the left and right bounds.
Yeah, like 7x squared to x squared, and then
It's really
7x.
bad, Olivia. Trust me. And then you need to define what the y range is here, what the y range is here, what the y range is here, and that's complicated. You have to find a million intersection points and be super careful. But we're not going to do that, right? What are we going to do instead? Okay. You know what? It'd be really nice right now if I found a way. They spoil. I hate that they spoil. Don't look. Stop. Do not look. Okay? Let me describe to you what the idea is. Maybe, again, we're going to do another one over here if we have the time. But what's the idea? The idea is these functions are all similar. Like, look at this guy and look at that guy. Let me write them down one sec. I would like to switch in a world where, you know, these functions are just a constant right now. You're probably like, what do you mean they're just a constant? Well, I'm smiling because this is like the coolest topic in Math 119, in my opinion. This beats all the topics that you're doing. So look at this right now. How can I make a new variable here that's going to be equal to a constant? This is a hard question. I think you can see it if I remove this right now. Look at this guy. And I want you to think, 1 second, just do a little bit of thinking. How could I massage this equation? It's not by multiplying by a constant or anything like that. I just need to shuffle this around, nothing else. I promise. Shuffle it around so that one side is equal to a constant. What needs to be done for that? Shuffle it around. One side needs to be equal to a constant. What are we thinking? Like something again equals to 1. I'm helping you a lot here.
Is it like y over x squared?
Because this equals to 1. Huh. And what do you know? His friend here, the 7x squared, could you do the same, Grace? For this guy, what would happen here? Do it again. What would be y over x squared? She texted me saying she. Okay, no worries, Leah. Okay, so y over x squared, Leah. What would this be here? Just just 7. That's it. So why does this make sense? Well, I'll tell you why. Because you basically want to map right now. I think I mentioned this. You want to map this region, okay? That looks absolutely disgusting. You want to map it to a new world right now that where it will look rectangular. That's what we want to do right now. If we're able to do that, then our integral is a joke. It will literally be between two constants here and between two constants here. And that's it. Our integral will be a joke. Think about that. So that's why I'm so obsessed in creating these constants. These are the constants that are going to be on these intersections here. Okay? So similarly for the other guy that is involved, I've hidden the substitutions. Look at the other guy one sec. We have y equals 8 minus x squared. Olivia, I want Olivia here. Y is equal to 8 minus x squared. And then the other guy here is y equals to a very similar form, 32 minus x squared. How can I get something again on one side equaling to a constant? Microphone to Olivia.
Will you just add x squared both sides?
Okay. So this is going to get me 8, and this is going to get me 32. Okay. We're almost there. So you know what? Why don't we let u equal y over x squared right now? So that this guy becomes u equals 1, and that this guy becomes u equals 7. And with a similar token, why don't we let v equal to y plus x squared, so that this guy here becomes v equals 8, and that this guy becomes v equals 32. Okay. And if we're in this space, you know what the integrand looks like right now? It looks like a joke. Look at this. If we paint the integrand now on the UV axis, u goes from 1 to 7. Okay, that is the u equals 7 line. That is the u equals 1 line. V goes from, as you can see here, from 8. I guess I'll write it here, from 8. And then that's going to be our 32, let's say. Bam. And you need to find literally the area of this box. That is the integral that you were trying to desperately do here. So I'll shade it in, what has happened. That's going to give you the same area over here after the transformation. Let me just put these side by side, I guess. I want to show you the plots. Okay? So we made a jump from this disgusting mess to this disgusting, so this simple thing. And this is the jump. How cool is that? Now you're not done yet. Don't get too happy. That's like a third of the work there. We still need a few pieces to this. But at least you have an integral right now that literally goes from 1 to 7 and from 8 to 32 in the du dv world. You see? At least you have that. But what goes here? What goes here? That's the problem, right? Okay, what goes there? The Jacobian. The Jacobian is not a very fun thing to calculate, but I'll show you. It's written like this. If you have the du dv here, it's written like this. dxy duv. That's how it's written. And if you want to calculate it right now, if it's in this order, if it's written in this order, you got to do a little bit of a determinant back from Math 115. And here's what the determinant says. If you write, again, it depends on the order that you write these, because these could have been different names. This could have been Z and X, right? And then this W and I don't know what. So it depends on the variable names. What will go in here. When we have a matrix, it's very natural. You see the X first? That's what's going to be here at the very top. You see the Y second? That's what's going to be here at the very bottom. You see the U first? That's what's going to be at the very top on the denominator, obviously. Whoa. I almost made a mistake. So U again will be in the denominator of the first one. V is going to be in the denominator of the second one. And then again, same deal on the bottom one. U is going to be here like this, and V is going to be there like that. And they will all make sense because what you're going to get when you do the products here, you're going to get a chain rule basically. It will all make sense. There's a chance I screwed this up. I don't trust myself. Let me just see. I did not. du dx, dv dy. Yep. Okay. Wait. Whoa. What? Oh, that's if you write it in this direction. Okay, you see the u's and v's are on the top and the x's and y's are on the bottom. That's if you write it this way. But we want, when we put this in, we want this, right? Patience. This sucks. Remember, this topic is difficult. Patience. So you're going to tell me what's the difference between these? They're just inverses of one another. That's it. Okay. So this is how you write this one, right? And yeah, we're good to go. Now, why would I want to calculate the other one that I had up there? Why? Because I'll tell you why. Do you have x as a function of u right now? Let me remind you. Do you have x as a function of u? Over here, you don't. If I was to isolate for x right now, this would suck, right? I can do it. But I can also do like the derivatives now opposite and then just invert my result at the very end. Like, you know, invert what I get and make that my Jacobian in the other direction because I need it in this direction, the Jacobian. And the reasoning is that these kind of cancel, right? And you get the integral in terms of x and y again. It's a chain rule. I told you, it's like an advanced chain rule for multivariable functions. Or if you want to think about it, a more advanced implicit differentiation going on. You know how this, when we did this, we wrote it as d dy of y, and we did dy dx, and these canceled. It's a more advanced version of this implicit differentiation where these now cancel supposedly. Okay, so it's just an overhyped implicit differentiation in a way. However, it's up to us to decide right now if we want to go this direction or if we want to rewrite this. Okay, I'll give you the other way you can go about it. Actually, why don't I get Grace to practice to write these out? Hold on. Grace, do me a favor and practice here writing these derivatives out now, following the left hand.
It'd be the partial derivative of u over x, and then partial derivative of u over y, and then partial derivative of v over x, and then partial derivative of v over y.
Beautiful. So it doesn't matter if you want to find this and then invert it, right? Like do the result to the -1 power. It's the same, right? Now, eventually you will need to change variables, like over here. If you go this way again, you will eventually need to find what y is in terms of u and v and what x is in terms of u and v. Might as well do that now, okay? Not be lazy and just do it right now. We have the functions anyway, so why not, right? So there's your substitutions. And one thing I can do here immediately is isolate for y. Y here is u times x squared. And y here is v minus x squared. So if I equate them, right, if I equate them, I can get what x is right now in terms of u and v, right? And that's one piece of the puzzle. So ux squared is equal to v minus x squared. I can bring that guy over there, get myself u plus 1x squared equals to v. And then you can see where I'm going with this, right? X is going to be the square root of v over u plus 1. That's what's going on. Okay. There we have it. So I'm just checking to make sure I did it all right here. Yeah. Okay, v is equal to y plus x squared. Isolate for y, that's v minus x squared, and then go ahead and solve. Okay. Yes, that's fine. All right. So we got what x is, right, in terms of u and v, which is awesome. Now you can do the same for y, right? And it's really simple now that we have that. If this is equation 1 and 2, let's say, and this is equation 3, actually, it's easier than that. Use these ones and just literally plug in 3 into either one of them. So I'm going to plug it into 1, okay? I'm going to plug 3 here into 1, and then I immediately get what y is in terms of u and v, of course. So y is equal to u, and then x squared is v over u plus 1. You can see it just becomes uv over u plus 1. Beautiful. That's it. There they are in all their glory. Now, do you want to work again in the direction of di x, di u, di y, di u, or do you want to work the other way? Since we already got these in this form, might as well just do the partial derivatives, with respect to the v's and u's, right? That's what we need anyways. So I need this, right? I'm going to help here a little bit. This x, I would write it as, before we do any differentiation, I'd write it as v u plus 1 to the -1 power. And then this is all being 1/2, right? So I would write it like this to help out with the differentiation a little bit, right? Because it kind of sucks. And then y, same deal, right? uv, and then u plus 1 to the -1 power. Okay, So I'll give you the next break here. What I'm going to do is second washroom break for whoever needs it, which is me, as usual. And I'm going to leave you a chance to do these derivatives on your own, okay, on a piece of paper. If you're sticking around, if you're taking a break, take a break. So I need these, okay? As you can see, I need these bad boys. Di-x, di-u, di-x, di-v, di-y, di-u, right? I need all of these. Di-y, di-u, okay? And I need di-y, di-v. So they're not that bad, you know, but they're a little bit time consuming. Okay, so I'll line them up here. Okay, whoever wants to do them on a piece of paper and verify, but that's what we have to do. All right, so I'm laying them out for you like that. Okay, and if you want to get them, there's the relationships, okay? Some product rules going on here and here, okay? Try them, and let's be back in like a couple minutes again, 3 minutes. Okay, and let's finish it off. So BRB, give them a try. So let's.
I'm not sure how correct mine are, but I did the 2 partials for the x's.
Okay. What did you get?
Do you want the final answer or just the steps?
You know what? Why don't I do it and we compare?
Oh, okay, yeah.
Okay. So if I do this, first I would do the derivative of v, right, with respect to u. So we have to be careful here because, one second here. So one of the things I got to pay close attention to is the fact that when I'm doing this partial, the v, again, I've taught you that it will be acting like a constant. So even though it looks like a product rule, it actually isn't, because this is a constant, right? It will just stick outside. And don't fall for that, because again, people do fall for this and they think, what am I going to do with the v? It's a constant right now when you're doing partials. It stays the same. You have like square root of v over here. And then you have this guy who's just a square root. And what's going to happen to him is he's going to drop a power. And when I do the derivative of the, okay, let's not forget the negative 1/2 though. He's going to drop a power. So he's going to become to the negative 3/2. And then the derivative of the inside is just 1. When this reaches inside, derivative of u with respect to u is 1. Derivative of u of 1 with respect to u is 0. So you just get 1 out of this. So in total, compare here, Olivia, to see if like what you did was right. But I would have the square root, okay? The 1/2 is coming outside anyway. So negative 1/2 square root of v divided by u plus 1 cubed. Something like that. Okay? So it's not like crazy bad, but it's like you got to keep an eye out who you're differentiating with respect to. You have to go at 9:30. Is it okay if okay, how do I want to play this? Let's pause 1 sec. Okay, so I just realized I wasn't recording for the part here that we did the derivatives in the Jacobian and we evaluated the integral. So I just want to again walk you through really quickly what happened. We have the answers on the screen, but essentially we took the derivatives again here, the partials of x with respect to u and v, of y with respect to u and v. And again, while you were taking them, I was just advising you to be careful. If you're taking the partial with respect to u, v, for example, will act like a constant. That's why you don't see it change over here. It's the same if you take it with respect to u, or sorry, with respect to v. You can see over here that this guy hasn't changed, right? He's acting like a constant to my partial. And it's similar for the y. You can see now when I'm taking it with respect to u, these guys are getting hit, but this guy acts like a constant and stays at the front here. Similarly, when I take it with respect to v, It's the u's that don't get hit, right? So that's why you see me write u over u plus 1 immediately, right? Because they don't get hit by the derivative. There's constants to it. And then the v's derivative is just 1, and it vanishes. So we've taken those partial derivatives, and you can see them here. They're end form. And I'm ready to put them in a Jacobian, which is just a fancy determinant of these derivatives. So there's the Jacobian, and we're plugging these in. And essentially, we get the matrix here with these partial derivatives done. 2 by 2 determinant here, not a big deal. We know how to do those. Just multiply these two, subtract these two, right? The product of them. We can see the products here. Okay. I did a little bit of algebra here. Again, if you're ever confused, to do the algebra here effectively, I always distribute the power of the square root into the things that I'm working in. So like this to me looks like u plus 1 to the 3/2. And then I'm multiplying it by u plus 1 to the 1. 3/2 plus 1 is 5/2. And that's why you see that here. So I always distribute that square root in. And that's why you see this to be v to the 1/2. Similarly, here it's the same deal. That's u plus 1 to the 1/2. And then over here, u plus 1 squared, that's 4/2. 4/2 plus 1/2 is 5/2. And that's what you see in the bottom. So, of course, they combine here in a nice way. If you pull outside the denominator and v to the 1/2, you get this. There's a factor of these that is canceling. And essentially, you get right now this as your final Jacobian. So you plug it in the integral now to evaluate it. That's what we found for the Jacobian. The bounds were already set earlier. And so to do this integral is very easy. We don't have variables in the integrand. I can just split the integral up into 2 right now, as you can see. And I evaluate this guy basically immediately. So it's v to the 3/2, but we got to cancel the power that comes down. So we multiply by 2/3. So I said, excuse me, the integral of this is v to the 3/2, but I have to cancel the 3/2 that's coming down from the derivative. So I multiply by 2/3. And the other one here, what I've done, I just did a quick double u substitution. It's a u substitution, but I'm already working with u. So I did a quick u sub. I called this w, as you can see here. The derivatives basically give me 1. And then I changed the bounds here too to do the integral immediately after the substitution. And when I put everything back, that is now w, that is dw. So you can see that I basically have 1 over w to the 3/2. I can bring the w upstairs and raise it to the power of negative 3/2. The bounds here have changed again, right, because of the sub. And then I just do the integral of this, which is another polynomial to my eyes. So this must have came from a negative 1/2 power. That's what you see me do here. But when the negative 1/2 comes down from the derivative, I need to cancel it. So I multiply by negative 2 to do that. That's what the antiderivative is. Then I evaluate the bounds that I have to do here, and that's what they look like. So this is the value of the area that you were trying to find between the original functions. I was talking to Olivia and Kelly after the other 3 of you left, and what we are doing for this one again, I encourage them to do it on their own. The hint was to do how to do the substitutions here. You're always trying to bunch the variables on one side and cause them to be equal to a constant. That's how you can find what substitution you need to use. So if y is equal to x here, a clever thing to do is again divide by the x to get a 1 on the right-hand side. And then you do the same here. You divide by the x and you get the 1/2. So it looks like the substitution here needs to be u, right? This y over x needs to be u. You could have called it v, of course. It doesn't matter, really. It's just names. But the first substitution is y over x, because that causes the one side here to be a constant. You're looking for that. The other one here has these. They have the same form. That's why I grouped them together. And how I can cause a constant again is by cross multiplying here and having y times x on one side. Y times x here is equal to 1. y times x here is equal to 2. So immediately I get what the other substitution needs to be. It needs to be yx, y times x. So once I have the substitutions, your next goal is to get, if you're doing this in my order, is to get what x is as a function of u and v and what y is as a function of u and v once you get the substitutions down, because now you have equations to work from. So you get these from combining these in some meaningful way. Now, once you have your functions of x and y in terms of u and v, you're ready to take their partial derivatives with respect to u and v and fill in the Jacobian. So once you fill in the Jacobian, you can do the determinant here, get what the Jacobian is going to be in terms of u and v, and then plug it back into the integral. And at that point, you're evaluating the integral. So I want you to try that example, okay? And the plan is for tomorrow to meet between this time to finish off the rest of the things I wanted to show you, which are one example on approximating. And I wanted to show you one more question on directional derivatives, which is really important and cool. And maybe whatever we've left off, like any questions you have from the examples of the triple integrals I've provided you with, or maybe if you were struggling on this one, maybe clarify a little bit what's going on. But that's the plan. So we're meeting for 1 hour or a bit less. Just clarify that. That is all. And again, I'll see you soon.